Hello and welcome to podcast number 46. This is one that's going to tie all the alkene reactions together. So in the previous podcast, we completed our spider charts. We have considered 12 different reactions that alkenes can do. And now the trick is to take these 12 reactions and apply them in synthetic pathways to figure out how to convert one molecule into another. And so the logic here is very powerful. And so the reality is 45 probably messed with your head and sort of put too much information, everything going around. 45, if I'm just being honest, wasn't very good. Luckily, 46 will come in and fix all the issues that 45 caused. And simple things. So whereas we finished 45 with chaos, 46 will hopefully take things and integrate it and make it a lot more sense. So using alkenes in synthesis. So one of the big reasons we're studying reactions is because we want to figure out a pool of information, a pool of reactions to build different molecules. So let's see where we start. So synthetic pathways, synthesis, starts with one molecule and finishes with another. Subtle differences in the structure become key in reactivity or what you need. So we have to figure out how to convert over. So your job is to recognize first what stays the same and then what changes and any telltale features you recognize because of it. So in the beginning, we have a bromine and a 6-carbon skeleton with a methyl. In the end, we still have a 6-carbon skeleton and we still have a methyl, but bromine is gone and two OHs have come in. So we have to do at least two things. We have to get rid of the Br and we have to add on two OHs. We only have 12 reactions from alkenes, but we also have elimination and substitution. So it's going to be really hard to substitute one OH for a Br and suddenly have a second OH appear. So we have to go through alkene chemistry. So if we look at the other thing, the other subtle thing that I didn't pay attention to that'll help me here, there is also an H that's got to disappear. So Br and an H have to turn into two OHs. Well, luckily, I know from earlier reactions that I can do an elimination. So I can do an elimination to get rid of an H and Br to form an alkene, and I know I can add two H's, and I need to pay attention to the fact that they are anti to one another. So specifically, I know how to add one anti. So inventory, what has changed? Count carbons. Carbons stayed the same number of carbons, that blue backbone. We did that. Look at the functional groups. Your functional groups have gone from Br to two OHs. And then look at the location. They are happening in the same spot. The H and the Br are on the exact same carbon as the two H's, which means it's probably passing through some alkene. Consider your regio and stereochemistry. Regiochemistry, we get the double bond forming here, not here. So we want the reactivity to be here, which means specifically for this one, I need it to be Zaitsev, not Hoffman, but Zaitsev elimination. And for this product, the OHs are anti to one another. So I need to go through MCPBA and treat it with water. Okay, so primary, secondary, tertiary matters, and just the alignment of what atoms are involved matter. Okay, syn and anti definitely matter. Irrelevant here, I need anti for elimination, but syn didn't happen, anti happened here, so I need to know it's anti-addition. And then enantiomers versus diastereomers, you have no chiral centers once you eliminate here. So I start with two chiral centers. When I get an alkene, it's going to be gone, and then I'm going to get two totally new chiral centers. But when I go from an alkene to this product, it's likely going to be enantiomers. Okay. Take inventory of your reaction database. You have to have an elimination. So in this case, E2 via Zaitsev. And then anti-OHs, which means peroxide. So substitution, not going to happen. So that one's gone. Redox, nah, it's kind of redox, but we're not really what we're doing. Elimination and addition, absolutely. So let me get rid of my words. But elimination, addition, you're doing E2 via Zaitsev. Elimination. So E2Z. In addition, we're doing peroxide. Actually, sorry, we're doing MCPBA. We're doing peroxy acid, followed by OH2. And then whatever conditions we need with it. So need Zaitsev elimination. So we need a small, strong base. So step 1 in OET. And then we need anti that. So epoxide formation followed by water. That was it. So your job is to fill that out. So actually, let me go back and okay. Unfortunately, I got to go through all the words. I just one time want to go through the steps and write it in. So I apologize that I changed my mind midway through when I'd already abandoned ship on this one. But just want to show those 2 steps the way we would do it. And each professor is different what they want. Some want the intermediate reactions. If you happen to be taking an OChem class, I'm teaching for a grade. And so if you're not watching these videos for review purposes for a standardized test or just, let's say you're coming back taking second semester organic chemistry after a long wait from first semester, so you might use it for that. But if you are actually enrolled class-wise, I am perfectly fine if somebody does this. Draws 2 arrows. The first arrow would be NaOET and HOET as solvent and heat, which could be represented with triangle. That's 1. And then step 2, 1 MCPBA. And then I'm not going to be really a stickler for solvent. And then H3O plus. So that is what you would have to draw to get full credit on this. You have to make sure you're specific with certain conditions. Heat matters for this one. No heat, you lose points. And then the region here, I should put in water. And MCPBA, not going to worry about solvent too much. Okay, so this is number 2. See how we do. So again, let's inventory the carbon chain. Carbon chain has gone 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Methyl, so that's all the same. This time, we started with the same compound, but we've now added anti once again, but we've added to the less substituted side. So hopefully you're taking a lesson learned from the first one. So inventory, same number of carbons, OH and OET, Austin H and Br. So those are the groups. You are dealing with secondary, not a tertiary. So you're actually going to anti-addition to 2 secondaries. So I'm trying to get my double bond in this spot over here. It's not a substitution reaction. You only oxidize 1 carbon, same thing as before. So it's basically the exact same thing we did before. Elimination, then addition. The only difference, it's Hoffman elimination. You're trying to get the double bond in a different spot than the previous question. So that part's the same, but now the double bond has to go there. That is the less crowded side. So we need to use a bulky base, hefty Hoffman. So hefty base like LDA, we go from here to here. I would add LDA and heat. And then from here to here, similar as before, oxidation, but instead of using water, so I'm going to use MCPBA, but instead of using acidic water, H+, I'm going to use H plus ethanol, my second step. Okay, third one, inventorying again, the ring structure, 6 and 5 has stayed intact, 6 and 5. There are no alkyl substituents to worry about, but we have lost an OH. We have gained CLs in an anti-fashion. Same number of carbons, same ring structure. Gained two OHs, lost an H, or gained two CLs, excuse me, lost an OH and an H. But location has changed. So in this case, I'm not really dealing with Hoffman versus Zaitsev. The double bond actually has to move to a completely different carbon than where the leaving group was. That has to be your intermediate because that's the one. I don't see it going forward. There's no obvious way to see that the double bond is here instead of right next to the leaving group. So this is what's called retrosynthetic analysis. Instead of looking at the reactant going forward, you're looking at the product and working backwards. So if you've ever solved a maze, sometimes you start at the beginning, go to the end, it's fine. But a lot of times you start at the beginning, you go and you hit this bottleneck, this dead end, this point you don't know what to do. And so you go to the end of the maze and work backwards. That's what we're doing here. Front of the maze doesn't help. Back of the maze, I know the double bond had to be here. So to get from here to here, we have to have a rearrangement. So tertiary, tertiary, anti-addition. So I know anti-addition, that reaction is going to be Cl2. I'm going to put an HCCl3. But as long as it's aprotic, it should be fine. That's going to give my anti-addition of two CLs. But to lead into that, I'm going to have to get rearrangement. Rearrangement only occurs under acidic conditions. So likely as an enantiomer, check. Up, down, and down, up. Not a substitution reaction. Oxidize at 2 carbons. Sure, doesn't help me. Once again, elimination followed by addition. The elimination with rearrangement. So we need to add something conditionally that will get those hydrides to shift. So sulfuric acid in water. That combination gets rearrangement. Cl2, anti has to be chlorine in an aprotic solvent. Again, I chose HCCl3 chloroform, but it doesn't have to be that solvent. Okay, these are going fairly well. You should probably consider modifying my checklist because if it's working, great. If it's not, then change the sequence. The key thing is you're recognizing these things. Make sure the carbon backbone stayed the same. If carbons move, then you have rearrangement. If carbon-carbon bonds are broken, you had ozonolysis. So it's paying attention to those details, followed by figuring out what went on and what came off. And you're going to find a lot of the early synthesis we do will involve elimination followed by addition. It's just very, very common. Okay, so synthesis. Here we go. We have a broken open ring. So it was bound to happen. We were bound to have that. So the carbon structure, same number of carbons, but it has broken the ring. So automatically, I know this is a result of the only reaction we know that can break a carbon-carbon bond, and especially recognize they gave me 2 double bond O's. So I'm going to redraw this structure to be the 6-membered ring. I'm going to do this group here. So 1 carbon coming up. I'm going to do this one, 2 carbons coming off. And then I'm going to connect them with a double bond because that's the double bond that's going to bring to form those 2 O's. So I need to go from here to here, meaning I need to get my double bond formed right there. Okay, so my logic. Those 2 tell me they were cleaved. That means it had to be, well, no stereochemistry, who cares? But not a substitution reaction, oxidize 2 carbons, definitely, so ozonolysis. Elimination, but instead of addition, elimination, then cleave. Got to cleave it. So we got to cleave this carbon-carbon bond and make 2 carbonyls. The elimination, Hoffman, because it has to go to this opposite side. The only problem with using a strong base like LDA, it sounds great, except the most acidic proton is on that O, and you're just going to end up deprotonating the O and create all sorts of issues. So we need to rethink our base or turn this into something else. So we learned early on that OH can be turned into different groups, such as OTS, CLBR, whatever you want to turn it into, but we have to convert it to something else first. So let me at least put this here. Ozonolysis step 1. Step 2 is methyl sulfide. So we have the two reactions, but this one, we actually have to do 2 steps. Turn it into a better leaving group. And so I'm going to put it as an OTS. So I'm going to add tosyl chloride and then LDA. So as long as I do that, as long as I make sure that I don't add a base to something with a protic hydrogen. So we're done. We've organized it. I'm hoping, again, there's a lot going on. 46 had a lot to clean up because we had all the stuff before. 45 is just all the chaos of all the reactions all being thrown at you in one sitting and saying, memorize this, just do it. Just like a dictator telling you, just know these 12. And so to overcome 45, we now looked at systematically how these reactions fall into place and hopefully see it more as a calming, big picture perspective. So I hope this is going well. Have an absolutely wonderful time studying these on your own, and I will see you at the next podcast. Until then, bye.